Okay, today we're going to learn about complex numbers, and we're going to learn about how to write the imaginary unit I as a complex number, how to add, subtract, multiply complex numbers together. Then we're going to learn something called complex conjugates. I'm going to use that to divide complex numbers. And then we're going to move this over to our quadratic, starting with our polynomial, starting with quadratic equations. So we have learned that some quadratic equations have no solution. For example, x squared plus 1. That, in fact, actually, it has no real solution, but it does have a solution. So to figure out what we have to do when we get a square root of a negative number, we use what's called imaginary unit I. So I is defined as the square root of negative 1. Okay, and if I equals square root of negative 1, I squared must be negative 1. So by adding real numbers to real multiples of the imaginary unit, we form a set of what's called complex numbers. We have a new number set called complex numbers. Each complex number can be written in standard form. The standard form of a complex number is A plus BI. So you have an imaginary number and a real number. So the A is what we call the real number, and that's just a number, 1, 2, 3, 4, 5, etc. And B is called imaginary number. Now these A and B can be any number. So it could be positive, negative, fractions, decimals, anything. So we're going to write the complex number negative 5 plus the square root of negative 9 in standard form. So square root of negative 9 is the same thing as square root of negative 1 times square root of 9. Square root of negative 1 is defined by I. Square root of 9 is 3. So we get negative 5 plus 3i, and that's in standard form. Notice the negative 5 is the real part, and the 3i is the imaginary part. Two complex numbers, let's say a plus bi, and, mistake. Two complex numbers, a plus bi, and C plus di, are equal to each other. Only if, so these two numbers are equal to each other, if and only if the real parts are equal and the imaginary parts are equal. So only if a and c are equal, and if b and d are equal to each other. That's the only way that you can have two complex numbers the same. Now let's say we have two complex numbers. These are not necessarily the same, and we want to add them together. So if you want to add two complex to number, you add the real parts together, and then you add the imaginary parts together. And if you want to find the difference of two real numbers, you can subtract the real parts, and then plus the difference of the imaginary parts. Or you can just distribute and combine like terms. I will do either way. So for this example, I'm going to do it as, distributing and combining like terms. So I'm going to start by distributing this negative to the first imaginary number or a complex number in parentheses. So that gives me a plus 12 minus a 3i, and then plus 3 plus 4i. Now I'm going to combine like terms. So the 12 and the 3 are my real numbers. They're like terms. And then I'm going to look at my complex numbers. So I'm going to start by combining my real numbers and then combining my complex numbers. And so I got 4i minus 3i plus 4i. Well, that simplifies down to just a 5i. So my answer to this problem is 15 plus 5i. Okay. So notice I did the exact same thing on this one, combining my real numbers and then combining my imaginary parts to get 7 minus 11i. So I hope you did well on it. Now, all the properties of real numbers correlate to our properties of complex numbers. So the associative property, the commutative property, the distributive property that you learned in previous sections, they apply to complex numbers just like real numbers. And if I wanted to multiply two complex numbers together, you simply use your distributive property, or sometimes referred to as the full method, first, outer, inner, last, if you have two complex numbers to multiply together. So that's all I'm going to do. To multiply complex numbers, you just use the distributive property or the full method. So looking at A, I'm going to use the distributive property. I'm going to distribute that 3i to each term. And then I see I have a 33i squared. Well, remember, I squared by definition is negative 1. So we always have to, every time you see an I squared, you have to replace it with negative 1. And so then I need to simplify down. And now my real part is the 33. So this is not in standard form because it has to be A plus BI. So the real part has to be written before the imaginary part. So I just rewrite this as 33 plus 15i. And now I have my answer in standard form. For B, on the other hand, I need to do the distributive property. So I'm going to do first outer, inner, and last, multiply my last terms together. And then combine like terms. And again, I see that I squared is equal to negative 1. And negative 12 times a negative 1 gives me a positive 12. And then combining my real terms together, I get 22 minus 7i. So I want you to try C on your own. Okay, so with C, in order to do this, I need to, again, do my distributive property. So I'm going to start by multiplying my first terms together, then my two outer terms, then my inner, and then my last terms. Combining my middle terms together, and they cancel out, and then replacing I squared with -1. Ooh, look what happens. I get a real number. So two complex numbers multiplied together can equal a real number. In fact, anytime you have what's called, if you have two complex numbers in the form of A plus BI and A minus BI, and those two numbers are called complex conjugates of each other. So anytime you multiply a number and its complex conjugate together, you will get a real solution. The i's will cancel out. So let's try that. Multiply 3 plus 6i by its complex conjugate. So the complex conjugate is 3 minus 6i. So I do the full method here and multiply it together. And we see that we have 45 as our answer. Now that we know how to multiply complex numbers together, abstract and multiply complex numbers, let's talk about dividing complex numbers. So that's when you have a complex number divided by another complex number. It'll be written as either a divide sign or, as I have here, as a fraction. So to write a quotient in standard form, you're going to multiply the numerator and the denominator by the complex conjugate of the denominator. So I'm not really changing the problem because I'm multiplying by a fraction with the same number on top and bottom. So I'm multiplying by 1. I'm choosing to write my 1 as a complex conjugate so I can get rid of the I in the denominator, so I can get a real number in the denominator, and then I can simplify it down. So let's look at 5a. So I need to multiply the top and bottom of this fraction by the complex conjugate of the bottom, which would be 1 plus 2i. So I'm going to do the full method on top and the full method on bottom. And see first, outer, inner, and last terms multiply together. Okay, combining my like terms on the, and we see that the middle terms on the bottom cancel out. And on the top, the 12i and the 7i can add together equal 5i. And I can replace every I squared with -1, so that changes it to a positive term. And then I can add, again, I have like terms. But I'm not quite done. I'm still not in standard form. So I notice I have a GCF on the top, so I can factor out that 5 from the numerator, and that leaves me with 4 plus I. And then the 5 in the numerator and the 5 in the denominator will simplify down, and my answer is 4 plus I. So that quotient is equal to 4 plus I. Okay, I'm going to pause and let you do B. So as you can see, the complex conjugate this time is just -2i because it's considered 0 plus 2i and 0 minus 2i because we just don't write the 0. So I'm just going to use the distributive property on the top, and then I'm going to multiply the two bottom together. Replace my I squares with -1, of course. And then we need to simplify. Well, again, I can factor out a GCF from the top, which is 4, and that leaves me with a -4i. Plus 8, and then so I have, if I write that in standard form, switching my terms over, I get 8 minus 4i. Hopefully that's what you ended up with. All right, now what if I wanted to add two quotient terms together? Well, to do this, you're going to do it just like you add fractions that you learned in elementary school, so you just need to have common denominators. So if you have a common denominator, you can add fractions together. And so I'm going to use the same thing here. So I need to have a common denominator between I and 4 minus I. And so that's just going to be the product of those two. So I times 4 minus I is going to be my denominator. So this first fraction I changed by multiplying by 4 minus I. So I need to do what I do at the bottom, I have to do the top. And then so I need to multiply the top of the second fraction by 3i, by I. Okay, so now I'm just going to write it as a single fraction using my distributive property on the top. And then minus my 3i for my second fraction. And then I end up with 4i minus I squared. Okay, let's combine some like terms. So I end up on the numerator as 4 minus I squared, and the denominator I have, and replace all my I squares with -1. And then simplify that down, I get 5 divided by 4i plus 1. But this is still not in standard form because I cannot have i's in the denominator in my final answer. So since the i's are not in my denominator, what I need to multiply this fraction by our complex conjugate because it's still not done. I'm still not done. So I'm going to multiply the top and bottom of this fraction by the conjugate of 1 plus 4i, which is 1 minus 4i. And then we're going to multiply again. And I get 5 minus 20i. over 1, and then the middle terms cancel each other out, and you end up with minus 16i squared, which just becomes 17. Now this time I do have a GCF on top, a 5, but if I factor the 5 out, it doesn't cancel out with the 17, so it doesn't help me any. So I'm just going to break up the fraction and rewrite each of those real parts over the over 17. So this is how you'd write the answer in standard form. Okay, let's talk about simplifying roots, the positive roots of real numbers. So the principal root is just the positive square root. So the square root, normally you have plus or minus the square root, just the positive square root is the principal root. So if you're asked to find the square root of negative a, that's the same as square root of a times square root of negative 1, or in the square root of negative 1 by definition is I. So we have I times the square root of a, or square root of a times I. Now the square root of a times I is in standard form, but if you want to write it the other way with the a first, that's okay, because you got to make sure the I is not underneath the square root. So you got to make your decision based on your neatness of your writing. So here I am multiplying these through, and I'm replacing every time I see I squared with a square root of negative 1 is an I. Now I need to simplify 48. So I'm doing a factor tree to help me simplify this down. And on the factor tree, what I'm looking at is I'm getting down to prime numbers and then finding all pairs. So I have 2 pairs of 2, so that means 2 times 2 comes out, which is 4. And I have a leftover 3 that stays underneath the radical. And so I'm going to do the same thing with the square root of 27. So I know 27 is 3 times 9, and 9 is 3 times 3. So I have a pair of 3s and 3 leftovers, so that becomes 3, the square root of 3. And so I have 4i, the square root of 3, minus 3i, the square root of 3. Now since these have the same radical, I can combine them together and subtract and get i, the square root of 3. Okay, hopefully you realize that the negative 2 plus the square root of negative 5 squared means I have to take this complex number times itself. Okay, so I'm going to start by rewriting my square root of negative 5 as I, the square root of 5. And I'm going to do this for birth terms. And then I'm just going to do my distributive property. So first terms multiply together, my outer terms, my inner terms, and my last terms. And square root of 25 is 5. Adding my like terms together. Remember, I squared is negative 1, so that becomes a negative 5. Combining 4 minus 5 is negative 1. And then if I want to write this in actual standard form, I put the I very end, make sure it's not underneath the radical. So I kind of put a tail on there to show that. And that's how you write complex numbers in standard form. Now let's apply this to polynomials. We're going to start with quadratics today, and eventually we're going to expand these out to all our polynomials in the next section. So if I want to solve a quadratic that cannot be factored, what I always go back is my quadratic formula. So you need to know this formula if you haven't not memorized it yet. So quadratic formula is x is equal to opposite b plus or minus square root of b squared minus 4ac all over 2a, where a is the coefficient of the x squared term, b is the coefficient of the x term, and c is the number by itself. So looking in this example, we're going to use the quadratic formula to find the solutions to 9x squared minus 6x plus 37. So I'm going to plug this into my quadratic formula. So opposite of b would be a positive 6, plus or minus the square root of b squared, so that's negative 6 squared, minus 4 times my a of 9 times my c of 37, all over 2 times a, which is 9. So I'm going to start by simplifying what's underneath the radical. So I'm going to do negative 6 squared, which is 36. And then I need to multiply negative 4 times 9 times 37, which gives us 1,332 over 18. And so I get negative 6 plus or minus the square root of negative 1,296 over 18. Now that negative underneath square root comes out and makes it an I. So I get 6 plus or minus I, the square root of 1,296 divided by 18. 1,296 is actually a perfect square, and it's actually 36 times 36. And now, oh, I got a common denominator, so I'm going to factor 6 out of the top. And then I can divide 6 into 18, which will go 3 times. And so I'm left with x is equal to 1 plus or minus 6i over 3, which I can then write it in standard form by breaking up the fraction. And 6 divided by 3 is just 2. So my solution is 1/2 plus 2i and 1/3 plus 2i and 1/3 minus 2i.